Welcome to our lecture on plate tectonics. Today, we are diving into the fascinating world of convergent boundaries, which is what happens when tectonic plates crash into one another. As we will see, the results of these massive collisions depend entirely on the types of crust involved. There are four main subtypes we will explore: ocean-ocean, continent-ocean, continent-continent, and continent-to-arc convergence. Let us start with ocean-ocean convergence. When two oceanic plates collide, the older, colder, and therefore denser plate subducts, or sinks, beneath the less dense plate. This plunging action forms a deep trench along the boundary. Above the subduction zone, a curved chain of volcanic islands emerges, known as an island arc. When you have a massive grouping of these islands, like in Indonesia, it is called an archipelago. How exactly do these islands form? As the oceanic plate, loaded with wet sediments, sinks into the hot asthenosphere, it undergoes extreme pressure and temperature. Around 100 kilometers deep, the rocks metamorphose and melt. This creates magma, which is lighter than the surrounding rock. Buoyancy forces this magma upward, leading to constant volcanic eruptions on the ocean floor. Over millions of years, these eruptions build up layers of rock until they break the ocean surface, creating an island arc. A perfect example of this process is the Philippine Island Arc system. Here, the Philippine Sea Plate is subducting underneath the Sunda Plate, which is a major continental shelf extending from the Eurasian Plate. This specific collision creates the deep Philippine Trench. The Sunda Plate itself is part of a larger region known as Sundaland, which was exposed land during ancient times when sea levels were much lower. Similarly, the massive Indonesian archipelago was formed by ocean-ocean convergence. In this region, the Indo-Australian Plate is subducting below that same Sunda Plate. This creates the Sunda Trench, with the famous Java Trench being a major section of it. Over millions of years, the constant volcanic activity builds up these islands so much that they begin to merge, slowly transforming oceanic crust into new continental crust. Moving to the Western Hemisphere, the Caribbean islands offer a slightly more complex scenario. The Caribbean Plate is mostly oceanic and moves eastward, while the North American Plate moves westward. This creates a transform boundary, but because they converged in the past, there is still subduction occurring. In the Lesser Antilles, the South American Plate subducts under the Caribbean Plate, fueling active volcanoes like Mount Pelée, famous for its devastating eruption in 1902. The Isthmus of Panama, the narrow strip of land connecting North and South America, also owes its existence to plate convergence. Originally, the ancient Pacific Farallon Plate subducted beneath the Caribbean and South American plates, creating a volcanic island chain called the Panama Arc. As the plates continued to shift, acquiring a north-south convergence, this Panama Arc collided with South America. The resulting uplift raised the land out of the sea, forming the isthmus. Japan is a fascinating case study because its volcanoes are part of three distinct volcanic arcs, meeting at a triple junction on the island of Honshu. In the north, the Pacific Plate subducts under the Eurasian Plate, forming the Japan Trench. In the center, the Pacific Plate subducts under the Philippine Plate. And in the south, the Philippine Plate subducts under the Eurasian Plate. The immense force from these plates actually tilted the Japanese arc eastward, opening up the Sea of Japan.
Have you ever wondered where the deepest part of the ocean is? It is the Mariana Trench, formed by the subduction of the Pacific Plate beneath the Mariana Plate. Its floor, the Challenger Deep, plunges about 11,000 meters down. However, because the Earth is a geoid, meaning it bulges at the equator and is flatter at the poles, the Challenger Deep is actually not the closest point to the center of the Earth. Parts of the Arctic seabed are closer.
Now let us shift to our second subtype, continent-ocean convergence, often called Cordilleran convergence. A cordillera is simply an extensive chain of mountains. This process is very similar to ocean-ocean convergence, but here a dense oceanic plate collides with a lighter, thicker continental plate. The oceanic plate subducts, forming a trench, but instead of island arcs in the ocean, this process builds massive volcanic mountain ranges right on the edge of the continent. As the oceanic plate dives down, it carries thick layers of sediment. Much of this sediment gets scraped off against the edge of the continent, piling up in the trench to form what we call an accretionary wedge. This compression leads to crustal shortening. Meanwhile, deeper down, the subducting plate melts. The resulting magma pushes up through the continental crust, erupting to form a continental arc, which is a chain of volcanic mountains on land, like the Cascade Range. This intense lateral compression does more than just create volcanoes. It causes orogeny, which is the geological term for mountain building. The buoyant continental crust is thrust upward by the advancing oceanic plate. The immense stress causes the rock layers to buckle and fold, creating a fold mountain system. Over time, as these mountains erode, the crust undergoes isostatic adjustment, meaning it floats higher on the mantle, eventually exposing the deep roots of the ancient mountains. The Andes Mountains in South America are the textbook example of continent-ocean convergence. Here, the oceanic Nazca Plate is subducting beneath the continental South American plate, creating the Peru-Chile Trench. The pressure from the accretionary wedge has folded the rock, raising the mountains to incredible heights. The Andes are still actively rising and feature intense volcanism, including Ojos del Salado, the highest active volcano on Earth, and Mount Aconcagua, the highest peak outside the Himalayas. Further north, we have the Rocky Mountains. Here, the North American plate moves westward, colliding with the eastward-moving Juan de Fuca and Pacific plates. However, unlike the steep subduction that formed the Andes, the oceanic plates here subducted at a much shallower angle. Because the plate slid further under the continent before melting, the Rockies formed at a significant distance inland from the coast, and the offshore trenching is much less obvious. Our third subtype is continent-continent convergence. This is a clash of the titans. Because continental crust is thick and buoyant, neither plate wants to sink. When two continental plates collide, there is no deep subduction zone like we saw before. Instead, the two massive landmasses crash together, buckle, fold, and thrust upward. The fragments of any remaining oceanic crust get plastered between them, welding the plates together in what is known as a suture zone. To understand the greatest example of this, the Himalayas, we have to go back 250 million years to the supercontinent Pangaea. Pangaea split into a northern landmass called Laurasia and a southern one called Gondwanaland. Between them lay a shallow ocean called the Tethys Sea. For millions of years, rivers dumped sediments into this sea. Amazingly, because these seafloor sediments were eventually folded and pushed skyward, the very summit of Mount Everest is actually made of ancient marine limestone. India was once a large island off the coast of Australia, part of Gondwanaland. About 200 million years ago, it began a massive northward journey, moving at a rapid pace of 5 to 6 centimeters per year. Around 40 to 50 million years ago, India slammed into the Eurasian plate. This violent collision squeezed the Tethys Sea out of existence, folded its sediments into the Himalayas, and thrust up the Tibetan Plateau. During this journey, massive volcanic eruptions also formed India's Deccan Traps. The Himalayas did not just pop up all at once. They are a series of parallel ranges that formed in distinct phases. The first phase, 50 to 40 million years ago, created the towering Great Himalayas. The second phase, about 25 to 30 million years ago, pushed up the Middle Himalayas. Finally, the outermost range, the Shiwaliks, formed in the last phase, between 2 and 20 million years ago. We even find similar fossils in the Shiwaliks in Tibet, showing their shared geological history. The incredible thing is that the Himalayas are still growing. High-precision satellite atomic clocks measure the mountains rising by 5 to 10 centimeters every single year. We also see evidence of this uplift in Tibet, where ancient lake terraces are now found high above the current water levels. Furthermore, the rivers in the region are in a youthful, highly erosive stage, and the frequent powerful earthquakes in northern India prove that the tectonic compression is far from over. The Himalayas are not the only mountains formed this way. The Alps in Europe and the Atlas Mountains in Africa are young fold mountains, created by the ongoing collision between the African and Eurasian plates. On the other hand, the Urals in Russia and the Appalachians in North America are ancient fold mountains. They were formed hundreds of millions of years ago by continental collisions that occurred even before the supercontinent Pangaea broke apart. When we look at the hazards associated with these boundaries, there is a stark difference. In continent-continent convergence, the crust becomes incredibly thick, up to 70 kilometers. Magma simply cannot penetrate this massive barrier, so there are no volcanoes. However, the immense friction generates disastrous, shallow-focus earthquakes. In contrast, continent-ocean boundaries produce both shallow and deep earthquakes, and because the continental edge is thinner, magma easily escapes to form highly active volcanoes. Our final subtype is continent arc convergence, perfectly illustrated by New Guinea. About 20 million years ago, the massive Australian continental plate pushed the New Guinea island arc northward.
This forced the Caroline Oceanic Plate to plunge underneath the island arc, forming the New Guinea Trench. Ultimately, the continental margin welded firmly against the island arc. Next time, we will explore what happens when plates do the exact opposite and pull apart as we look at divergent boundaries. Moving right along into the specifics of volcanism, let's look at where it actually occurs. Volcanism is primarily observed in continent-ocean, or CO, convergence zones. As the denser oceanic plate subducts beneath the continental plate, the immense heat and pressure melt the subducting plate and its metamorphosed sediments. This melting generates magma that rises to the surface, creating active volcanic arcs. But what happens when two continental plates collide? Interestingly, volcanism is almost entirely absent in continent-continent convergence. The reason comes down to the sheer thickness of the continental crust in these collision zones. Even if magma is generated deep below, the crust is simply too thick for it to break through. Instead, the magma remains trapped and stocked deep within the crust, slowly cooling underground rather than erupting. Now, consider divergent boundaries, like mid-ocean ridges. A common question is why, despite extensive volcanism, we don't see volcanic islands forming right along these ridges. The answer lies in the type of magma. Divergent boundaries produce basaltic magma, which comes directly from the mantle. This magma has very low silica content, making it highly fluid or low in viscosity. Because this basaltic magma is so fluid, it doesn't pile up. When it erupts, it flows outward over incredibly long distances before it finally cools and solidifies. This lateral movement is exactly what drives seafloor spreading. It creates broad, flat fissure eruptions or shield volcanoes, but it spreads out too much to build the tall, concentrated peaks required to form volcanic islands above the ocean surface. On the other hand, the magma found at convergent boundaries behaves completely differently. Here, the magma is andesitic or acidic. Because it is formed from the melting of crustal plates rather than mantle rock, it has a much higher silica content. This high silica concentration makes the magma highly viscous, meaning it is thick, sticky, and highly resistant to flow. This high viscosity changes everything about how the volcano forms. Because the andesitic magma is so thick, it cannot travel far. It moves slowly and solidifies very quickly around the vent. Over time, successive eruptions build layer upon layer of hardened lava and ash in a confined area. This vertical growth creates the classic steep-sided conical mountains we know as stratovolcanoes. This brings us to a fascinating geographical anomaly. If divergent boundaries produce fluid basaltic magma and shield volcanoes, how do we explain Mount Kilimanjaro and Mount Kenya? Both of these famous peaks are located near the East African Rift, which is a divergent boundary. Yet they are towering stratovolcanoes, not flat shield volcanoes. To solve this puzzle, we must remember a fundamental rule. The formation of stratovolcanoes versus shield volcanoes depends entirely on the silica content, and therefore the viscosity of the outpouring magma. It does not strictly depend on the tectonic location itself. The type of rock melting to form the magma dictates the final shape of the volcano. Mount Kilimanjaro and Mount Kenya actually formed at a distance from the main rifts during the creation of the African Rift Valley. The region was subjected to immense faulting and crustal stress. This extreme mechanical stress caused the subsurface crustal layers to melt. Because it was crustal rock melting rather than mantle rock rising, it produced highly viscous, silica-rich andesitic magma, resulting in towering stratovolcanoes. We can contrast this with the Ethiopian highlands in the very same region. The Ethiopian highlands formed directly along the diverging boundary at the East African Rift and the Afar hotspot. Because the magma here welled up directly from the mantle through the diverging plates, it was basaltic. This resulted in massive outpourings of fluid lava, creating extensive shield volcanism rather than isolated conical peaks. We will explore how these different volcanic structures impact local ecosystems next. Moving to the third stage of rift evolution, we see the formation of a linear sea. As the Rift Valley deepens due to continuous divergence, the thinned continental crust is eventually replaced by dense oceanic crust. This depression allows ocean waters to flood in, creating a narrow, linear sea, much like the modern-day Red Sea. The original rift valleys evolve into active volcanic vents, and the block mountains that flanked the rift transform into oceanic ridges. Because new crust is constantly being created here through seafloor spreading, this divergent boundary is known as a constructive edge. If a rift valley forms deep within a continental landmass rather than near an ocean, it can lead to the creation of rift lakes. As the land subsides along the fault lines within the rift zone, a deep basin is formed.
Over time, rainwater accumulates in these depressions. Because they are created by tectonic faulting, rift lakes are typically bounded by large, steep cliffs along their margins. It is no coincidence that the largest and deepest freshwater lakes on Earth are mostly rift lakes, born from this exact tectonic process. A prime example of a rift lake is Lake Baikal in Siberia, which sits right in an active rift valley. It holds the title for the deepest lake in the world, plunging to a staggering depth of 1,642 meters below the surface. But its depth isn't its only record. It is also the largest freshwater lake in the world by volume. In fact, Lake Baikal alone contains roughly 20% of the entire world's unfrozen surface freshwater. Another monumental rift lake is Lake Tanganyika. It is located in the Albertine Rift, which is the westernmost arm of the active East African Rift system. Lake Tanganyika is a lake of extremes. It is the world's longest freshwater lake, the second largest by volume, and the second deepest lake in the world, reaching depths of 1,470 meters. Its elongated shape perfectly mirrors the linear fault lines of the rift valley it occupies. Not all rift lakes are in currently active rift zones. Take Lake Superior in North America, for instance. It is the largest freshwater lake in the world by surface area, and it lies within the ancient and now dormant mid-continent rift. As a quick side note, the world's second largest freshwater lake by surface area is Lake Victoria, which is also associated with the tectonic activity in East Africa, sitting between the two main branches of the East African Rift. Finally, we reach the fourth stage, where a linear sea transforms into a full-fledged ocean. At this point, there is an intense outpouring of basaltic magma, which accentuates seafloor spreading. The oceanic crust completely replaces the old continental crust, and a mighty ocean basin is established. All major oceans today are at this stage. It is important to remember that the Earth isn't expanding. The new crust formed along these divergent mid-oceanic ridges is perfectly compensated by the destruction of older crust at convergent boundaries, constantly reshaping our planet's surface. Now, let's look at one of the most famous geological features on Earth, the Great Rift Valley. This massive fracture in the Earth's surface runs north to south for approximately 6,400 kilometers, stretching all the way from northern Syria down to central Mozambique in East Africa. Before the actual rifting began, this region experienced enormous eruptions of continental flood basalts, which were accompanied by the significant uplift of the Ethiopian, Somalian, and East African plateaus. If we trace the Great Rift Valley from north to south, its northernmost section forms the Bekaa Valley in Lebanon. Moving farther south, the valley becomes the channel for the Jordan River, which flows down into the Dead Sea on the border between Israel and Jordan. Continuing southward from the Dead Sea, the Rift Depression is filled by the waters of the Gulf of Aqaba and, eventually, the expansive Red Sea. As we move south from the Red Sea, we hit a geological hotspot, the Afar Triangle in Ethiopia and Eritrea. This is the location of a triple junction, a place where three tectonic plates are pulling apart. From this junction, the rift branches out. One branch continues eastward as the Gulf of Aden, extending into the ocean as the Mid-Oceanic Aden Ridge. Another branch heads southwest, continuing into the continent as the East African Rift. As the fault continues southwest as the East African Rift, it literally splits the older Ethiopian highlands right down the middle. Further south in eastern Africa, the valley divides into two distinct branches that wrap around Lake Victoria. The Eastern Rift, also known as the Gregory Rift, includes the Ethiopian and Kenyan rifts. The Western Rift, or Albertine Rift, contains a string of deep lakes, including Lake Tanganyika, and further south, the valley of Lake Malawi. The East African Rift is an incredibly active continental rift zone. It is the very site where the African continent is actively splitting apart. This tectonic process isn't new. It began developing around the onset of the Miocene epoch, roughly 22 to 25 million years ago. While geologists historically considered it just one segment of the larger Great Rift Valley, it is now studied closely as a prime example of a continent in the middle of breaking up. The East African Rift is fascinating because it allows us to observe different stages of rifting simultaneously along its length. In the south, where the rift is relatively young, the rates of extension are low. Here, faulting occurs over a wide area, and there is limited volcanism and seismic activity. However, as you move north towards the Afar region, the entire Rift Valley floor is covered with volcanic rocks. This indicates that the lithosphere here has thinned drastically, almost to the point of complete breakup. What we are witnessing is the development of a new divergent tectonic plate boundary. The main African plate is in the process of tearing into two distinct plates, the Somali plate to the east and the Nubian plate to the west. They are separating at a rate of 6 to 7 millimeters annually. As this extension continues, geologists predict that a complete lithospheric rupture will occur within the next 10 million years. The Somalian plate will break off entirely, and a brand new ocean basin will flood the gap.
This massive tearing of the Earth's crust naturally leads to significant geological surface manifestations, primarily volcanism. The East African Rift Zone is dotted with numerous active and dormant volcanoes. Famous peaks like Mount Kilimanjaro in Tanzania, which is a dormant stratovolcano boasting 3 distinct volcanic cones, and Mount Kenya, an extinct stratovolcano, owe their existence to this rift. Even though these specific mountains sit slightly outside the main valley floor, they were created by the magma falling associated with the East African Rift.
Alongside volcanism, the East African Rift is currently the largest seismically active rift system on Earth. The continuous stretching and faulting of the continental crust generate frequent earthquakes. The majority of these seismic events, and particularly the largest earthquakes, are concentrated near the highly active Afar Depression and along the major fault lines that define the edges of the Rift Valley. To wrap up our discussion on divergent boundaries, let's review the key takeaways. Divergent boundaries are the engines that create new seas and oceans. The process is a clear progression. It starts with upwarping and faulting, develops into a rift valley, floods to become a linear sea, and eventually expands into a vast ocean. Along the way, continental rift valleys can form deep basins that host some of the world's largest freshwater lakes. Finally, we can see this entire process in action today along the East African Rift, which is slowly but surely splitting the African continent in two.